Section 5.1. Section 5.1 starts talking about normal distributions. Okay? Normal distributions have a pretty specific definition, as you can tell by looking at the word definition. Okay? There's a whole box, a whole red box in your book, in your textbook, or you can get to the textbook online, remember that, about normal distribution. Okay, so we're going to take just a couple minutes and go through this stuff just to make sure that you understand what's going on. Okay, a normal distribution is a continuous probability distribution for a random variable. Okay, the graph of a normal distribution is called the normal curve. The normal distribution has these properties. All of these properties are true in a normal distribution or graph. It's called a normal curve. Okay, number one, mean, median, and mode are all the same. It's the same number. Mean, median, mode. Every single one of those are the same for a normal curve. Okay? The normal curve is bell-shaped and is symmetric about the mean. Wherever the mean is, or the median or the mode, because you know they're all the same, okay? That is what the bell-shaped curve is symmetric about. Okay? Now, for a long time, I never thought that was a bell. I have to be honest with you. I thought it's just like a mountain or something, right? But if you picture like a stick hanging up. I played handbells before. I don't know if you've played handbells before, but if you have like a stick, like right there or something, well, right there, and you bang the bell, right? Okay, so you guys are more creative than I have when it comes to imagining things like that. Are you okay with it being called a bell-shaped curve? Okay. The total area under the normal curve is equal to 1. Why? Because that's where we're going. Okay, the area under this curve is 1. The normal curve approaches but never touches the x-axis as it extends further and further away from the mean. So in both directions, it's approaching that x-axis but never touching. What do you know that would be called right there, algebra-wise, at the x-axis? Yeah, it's an asymptote. Okay, kind of, cross-curricular kind of word, even though they're both math, right? Between, remember what this is called? Mu, and remember what this is called? Lowercase sigma, right? Okay, so between mu minus sigma and mu plus sigma, which is the center of the curve, okay, the graph curves downward. So think about this with me for just a second. Between here and here, and here and here, the graph is curving downward. The graph is curving downward. Does that make sense? The graph curves upward to the left of this and to the right of this. Where it changes directions is called the inflection points. Can you see that this is curving downward, but this is curving upward? It's kind of weird, but it's kind of semantics. We got to make sure we understand the words. You okay with that? Okay. You've learned that a discrete probability distribution can be graphed with a histogram. Remember when we talked about histograms? Okay. For a continuous probability distribution, you can use a probability density function, which is sometimes abbreviated as PDF. All right. Now, there's a really beautiful function right down here at the bottom of this page. Isn't that really beautiful? A normal curve with a mean of mu and a standard deviation of this can be graphed using that function. You know me, I love algebra. I think that's a pretty cool function. I just have to remember what everything means, right? Okay. A normal distribution can have any mean and any positive standard deviation. Using these two parameters, we can figure out the shape of the normal curve. Okay? The mean gives the location of the line of symmetry, right there, right there, and right there. And the standard deviation describes how much the data is spread out this way. Okay? So if we're looking at this first one, notice it has a mean of 3.5, but please notice the second one also has a mean of 3.5. That's where the line of symmetry is, on the number line at 3.5. Okay? But notice the different standard deviations. This one is bigger. 1.5 is bigger, so this is more spread out this way. This standard deviation is 0.7, so it's closer together. Does that make sense? Now notice these last two have exactly the same standard deviation, so they kind of have the same shape, but notice where they lie on the number line. This one has a mean of 3.5, so its line of symmetry is at 3.5. This one has a mean of of 1.5, so its a line of symmetry is at 1.5. Does that make sense? Okay, so let's look at example 1 right here. Which normal curve has a greater mean? Now, when you first look at this, you might think A has a greater mean because it's higher. Okay, don't think about it that way. Okay, see how this goes up higher? That doesn't really make any difference. We're saying which one has a greater mean? Where is the line of symmetry further to the right on the number line? That's why A has the greater mean. Not because it's taller necessarily, just because it's further to the right on the number line. Which one has a greater standard deviation? B, because it's more spread out. Why? It's wider. Okay? Any questions about that? You got that okay? All right. If you look through example 2 in your textbook, on your textbook tab in your computer, it just gives you other things to think about and interpret based on the standard deviation or the normal deviation, that's given to you. Okay, so those might be good to look back at if you need to. All right. Then we have something called the standard normal deviation. Okay. Now, standard normal deviation is when the normal distribution has a mean of 0 and a standard deviation of 1. Okay, so the mean is at 0. That's where my line of symmetry is, and each standard deviation is 1. So if we're talking about 1 standard deviation or 2 standard deviations or 3 standard deviations away from the mean, we're just going by whole numbers. That's the standard normal deviation. Okay, now you've actually done this already. When we did section 2.5, we found a z-value. Do you remember a z-score, a z-value? Do you remember finding that? Yeah? The other thing it was called, let me show you for you visual people. Okay, 2.5, 2.4. When we talked about, right here, oh, you can't see that. The standard score. We found Z already, standard score or Z-score. Do you remember talking about that or doing examples on that? Okay, so that's going to come into play here because we're going to have to find Z, right? So yes, the definition was back here in 2.5, but they have also put it here since we're talking about it again here in 5.1. Okay, so the standard normal deviation is the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. What's the area under the curve? 1, right? And any area under a normal curve is 1, but they're just reiterating that for you in that sentence right there. Okay, standard normal distribution, the area under of its curve is 1. All right? Excuse me. When each data value is normally distributed, how about distributed? Sorry about that. Random variable x is transformed into a z-score, the result will be a standard normal distribution. Okay? After the transformation takes place, the area that falls in the interval underneath a non-standard normal curve is the same as that under the standard normal curve with the corresponding z boundaries. Okay? Empirical rule is also going to come back into place. Remember what the empirical rule was? What was it? 68, 95, 99.7, right? Remember empirical rule? Do I need to turn back to that real quick? Section 2.4. Empirical rule. Remember that? 68, 95, 99.7. Remember that picture? We talked about that one quite a bit. Okay, that's going to come back into play again today. All right, so either bookmark that on your textbook or draw it for yourself so you can have it in your notes ready to be used if you need to. Okay. Empirical rule is used to approximate areas under a normal curve when the values of the random variable x correspond to -3, -2, -1, 1, 2, or 3, or standard deviations from the mean. Okay? We've talked about different standard deviations from the mean, so I thought you guys would be okay with that. Are you? Yes? Okay. So after you use the above formula to transfer x values to a z-score, then you can use the standard normal table, which I'll show you in just a second, and that will help you. The table lists the cumulative area under the standard normal curve to the left of z for z-scores, and the z-scores go from -3.49 to 3.49. Why? I don't know. Okay? I told you I'd be honest with you from the very beginning. I just know that's what it says. But as far as why is it that, I just don't know. Okay? If you figure it out, I would love to know. Just for the record. Okay? All right. Properties of the standard normal distribution. Okay? The cumulative area for close to 0, so close to 0 for z-scores. So does it make sense that my z-score over here would be kind of close to 0? Let me start again. If my z-score is -3.49, so that would be over here. Does that make sense that -3.49 would be over here? Because -3 is right there. That z-score. Would it make sense that the area under the curve up to there is close to 0? Yes? Okay. What about the cumulative area if we're talking about when z is 0? What do you think the cumulative area would be then? When my z-score is close to 0, so right there, what's the area under the curve? What's the total area under the curve? 1. So how much of it did I just cover up? Half, right? So what's the area left under the curve when my z-score is 0? Half, 0.5. That's exactly right. Okay? What do you think the area under the curve is going to be when the z-score gets really close to 3.49? Like over here. How much is left? Right there. 1. Right? So if I start over here and I'm trying to find the area to the left, how much area is to the left? Nothing, right? If I go to halfway through, how much area is to the left? Half. And if I go all the way here to positive 3.49, how much area is left? 1, right? The whole thing is left, all right? The cumulative area increases as the z-score increases. Is that even logical? It's completely logical, isn't it? As I go this way, as my z-score is increasing, do you see that the area under the curve would be increasing? Yes? Okay. Now, from here to here, it's going to be increasing faster than if I was increasing from here to here, right? Just because this line is is steeper than something over here, right? Okay. Any questions about that? Okay. If you have a textbook, in the back of the textbook, okay, it's not in the back of this textbook, but it's in the back of almost every other single textbook. There's like a fold-out thing. Like this thing back here would fold all the way out. Okay? On one of the fold-outs is a z-table. And it looks like it's also back here at the back. So let me find it real quick. Yeah, it's table 4. So this one doesn't have a fold-out. It has just a table 4. It's 2 pages. There's the first table 4 and there's the second table 4. Okay? Notice where this z starts. -3.4. So that's to the very far left of my normal curve, right? So as it goes down the table, can you tell that I'm increasing the area? Yeah? Okay. This other table starts at 0 and guess where it goes? 3.4, right? So as I go down the table, I'm getting more and more area under the curve, right? So here's what we have to do. Here's how to read this table. If I say my z-score is 3.47, -3.47, I go here to -3.4, and then I go over to 0.07, because wouldn't those two together be negative 3.47? So if I'm saying what is the area under the curve at negative 3.47, my area is 3 ten-thousandths, right? Tenths, hundredths, thousandths, 10,000ths, or 0.0003. That's the area under that curve. Okay? What if my z value is negative 1.65? Well, here's negative 1.6, and then I go over where? To 0.05. So the area under the curve at that z value, negative 1.65, is 0.0495. So I guess really the hardest of this, once you have your z-score, is figuring out how to read the table, right? What if my what if my z-score was 2.74? 2.7, 0.04. So right there. You guys okay with that? Understand how to read the z-table, or the standard normal distribution table. Okay? If you do not have one of these tables, you need to let me know, because I need to get you one. Okay? I'll get you a hard copy that you have. 1, 2, 3, 4, 5, 6, 7. Okay? All right? Can you get it online? Okay? Thank you. I just know that some people might want to have a hard copy, and if you do, I will get you one. Okay? Yes? Okay. So, on the next page of your textbook, on to page 238, it walks you through trying to find cumulative areas when you know the z-score, which is what I just did with you. Does that make sense? Okay. So here's some examples through there if you wanna look at that. But there are some guidelines that we need to talk about. Okay. Because there's more than one way to find area under the curve. There's more than one place that you might want to find area under a curve. Okay. I might want to say my z-score is 1.23, and I want to find the area to the left. But what if I wanted to find the area to the right of 1.23? Well, what is my z-score going to tell me? That table I just showed you about, table 4, that's going to tell me the area to the left under the curve, isn't it? Yes! Can't I take it and subtract it from 1? If I know this area and I'm trying to find this area, and I know the area under the curve is 1, couldn't I say 1 minus the blue area? Yeah, right? Because that's what it's asking for in this particular example right here. It's asking me for this blue area. I can't tell that by looking at 1.23 on the table. What I can do is look at 1.23 on the table and subtract that value from 1, like it says right there. Yes? Okay, one more way is finding areas between two z-values. Well, any ideas? So I need to find the area under the curve from 1.23, which will tell me all of that. I need to find the area when my z-value is negative 0.75 and subtract it from the first one. Wouldn't that give me the blue area? Yes! Good. You guys seem excited about this. I need you to calm down some, though. Okay. All right. But those are the guidelines. Again, this guideline section is in your textbook, so if you need to look back at it, please do. Okay? So that's finding the area under standard normal curve when you're trying to find the area to the left and to the right. And then there's one on the next page that you find in between. Those are just examples you can go back and look at if you need to. Okay? Because the normal distribution is a continuous probability distribution, the area under the standard normal curve to the left of the z-score gives the probability that z is less than the z-score. So, for instance, in example 4, which I didn't talk you through, but it's this one right over here, okay? In this particular example, they looked it up on the table, and from the standard normal table, the area is equal to 0.1611, okay? So if we're trying to find the probability of that happening, let's look at this real fast. For example, in example 4, the area to the left of z was that, right? So the probability that z is less than negative 0.99, which was the z-score, is what? The same as the area, which is read as the probability that z is less than negative 0.99 is blah, blah. It's just translating the math to English for you. Okay. Now I think that's pretty cool. Okay. I think it's pretty cool that the area under the curve of your z-score is also the probability that z would be less than that number. Okay. But what if we're trying to find if it's to the right of that number? What's the probability if it's to the right of that number? How do we figure that out? Subtraction. Yeah. Just like we did area before. All right. Do you have any questions about that? Because that's the end of section 5.1. These are all just example problems right here. Okay. 5.2. Oh, look, probability. Kind of something we just started talking about right now, okay? Finding probabilities for normal distributions. You got to find a z-score. That'll help, won't it? Let's talk through this problem real quick, so I think that'll help understand what I'm talking about, okay? A survey indicates that people keep their cell phone an average of 1.5 years before buying a new one. The standard deviation is 0.25 year. A cell phone user is selected at random. Find the probability that the user will keep his or her current phone for less than 1 year before buying a new one. Assume that the lengths of time people keep their phones are normally distributed and represented by the variable x. Okay? So the first thing they did is they gave you a figure to look at. You know this. You know that the mean is the line of symmetry, right? So they put that right there at 1.5. You also know that the standard deviation is 0.25. So they went over here to 1. The shaded area for x less than 1, right? We're trying to find that. The z-score that corresponds to 1 year, how did we figure that out? Well, we just put it in the equation, right, that we talked about at the beginning of 5.1. So the x value, or 1, which is what we're trying to find, minus the mean divided by the standard deviation. That's negative 2. Okay, so standard normal table shows that the probability that z is less than negative 2 is right there, right? The probability that the user will keep his or her phone for less than 1 year before buying a new one is that. Okay, because let me take you here real quick and show you where it came from, because it's not really very clear. Table 4, negative 2. Oops, this is table 3. Every single time I look at this, I think it's saying Poisson distribution. I'm like, I don't want anything to do with that. But that's not really what it says, just for the record. Okay? Negative 2. Whoops. 0.0228 for negative 2. 0.0228. That's where that number came from. Does that make sense? Okay? So the interpretation is that 2.28% of cell phone users will keep their phone for less than a year before buying a new one. Now, also because 2.8% is less than 5%, this is an unusual event. What makes something an unusual event? It's a certain amount of thing, right? It's a statistic, right? It's a thing. You may want to look back at your notes for that. Okay? Yes, certain amount of standard deviations from the mean, right? So just be careful of that. Just watch out for that. Any questions? Here's the best part of this. Here's another example. Example number 2 talks about another survey, some time that we're shopping. And then example 3, it talks about using technology. I'm pretty sure that there's a way to find that stuff in the computer, on the computer, like it said. My concern is that it'll do it now for your homework, but it may not do it for the test. Like there was something last time that did that. Okay, so I am still looking into how to do it on our calculators, because it gives you clues and stuff about how to do it on the T84, but we don't have those. We have Inspires. Okay, so if you have already figured it out, I would love to know. I just have not looked into it yet for you, but I will. Okay, probably what I'm going to do is type it into Google or YouTube. All right, especially for stuff like this that I just don't know. All right. But the best part about 5.2 is that's it. Now it's just the example problems. Okay, so it mainly talks about probability. It mainly talks about finding the z-score and then using that as the probability, almost like word problems. This really kind of focused on word problems 5.2 did. Okay, any questions?